In this video, we'll look at expanding Euler's method to apply it to systems of ordinary differential equations. After studying this video, you should be able to apply an initial value problem solver to a system of ordinary differential equations. We'll do this for Euler's method, but the approach generalizes to any initial value problem solver. You should also be able to write a higher order ordinary differential equation as a system of first order differential equations, and implement Euler's method for a system of differential equations in MATLAB. Many practical problems require the solution of a system of differential equations. As we discussed before, we would write that system as dy1 dt is equal to f1, some function of t, y1, y2, and however many other dependent variables we have in the system. We would also need n initial conditions, y1 at t0, y2 at some t0, down to yn at some t0. Higher order differential equations can also be written as a system of first order differential equations. So in addition to applications where we're directly modeling some system, some physical system with a system of differential equations, we'll also solve higher order differential equations by first writing those as a system of differential equations. And we'll see an example of that in a moment. So let's look at expanding Euler's method for a system of ordinary differential equations. So basically, we will have just, if we have n equations, we'll have n y values that we're solving for at each time step. And for each one, we will evaluate that function now, which would be dy dt, where this is yi, is equal to some function of t, y1, y2, etc. And we've written some function to return that, an anonymous function in our MATLAB code. We've got some function dy dt that returns a column vector of derivative values. So let's look at how that works in an M file to implement Euler's method. So the first thing we need to do is figure out how are we going to keep track of our y values, and the way that we're going to do it, and mostly doing it this way because this is how MATLAB's ODE solvers are set up as well, is we can imagine our t values, we can imagine building a table basically with our t values here, y1, y2, etc. onto yn, all as columns in a matrix. So our y values are going to be in a n by, we'll call it n equation matrix, where n, the first n here is the number of time steps, and the second is the number of equations. So you can see that over here in the M file, where we're setting up y as, with the ones function, pre-allocating y for our solution as a matrix with n rows, one row per time step, and n equations, one column per equation. And then we'll set all of the first row equal to that initial condition, and then start our iteration through the time steps. So just like before, we have for I equal 1 to n minus 1. Now the difference here is at each time step we'll calculate dy dt at that time step, but this dy dt that we calculate from y is going to be a column vector because that's how we wrote our dy dt function up here. And then when we calculate yi plus 1, we're going to calculate all columns for the next time step. So when we do that, we'll take all columns from the previous time step, and then dy dt. Now one note, since we're doing all columns, this yi plus 1 colon, this is a row vector. So when we add these together for the matrix dimensions to match, we need to transpose the dy dt result because that came in a column vector. So we'll transpose that, multiply it by h, add it to all of the columns for the ith time step of y, and then move on to the next iteration. So I'd encourage you to download the Eulersys.m code, run it along with the following example, and make sure you understand how this is working. Use the idea in this example of writing a higher order differential equation as a system of first order differential equations. So given the initial conditions, y at 0 is equal to 1 and y prime at 0 is equal to 0, we're going to solve the ODE below from t equals 0 to 4 and plot those results along with the exact solution, which is y is equal to cosine of 3t. So let's start by writing this as a system of first order differential equations. And the way to do that is we will define some y1 equal to y and y2 is equal to dy1 dt. So those will be our first differential equations. So this would also be equal to dy dt. So now we can use that to rewrite this equation. So now the second derivative of y with respect to t would be equal to d by dt of dy1 by dt or dy2 by dt. So rewriting this equation now, we have dy2 by dt plus 9y1 is equal to 0. Now we need to put that in the form. Remember, our general form for Euler's method is dy sub I dt is equal to some f of t y. So doing that, we would have dy1 dt is equal to y2, and that's just what we defined right here. And then we would solve this equation here for dy2 dt, and we get dy2 dt is equal to negative 9 y1. And that gives us now a system of two first-order differential equations. And we can then use that to solve the system in MATLAB. So here's the MATLAB code to solve this system. We're going to solve it with two different values of the time step, h1 equals 0.1 and h2 equals 0.01 over that time span from 0 to 4. So here's the anonymous function that defines our system of ODEs. So y prime being a variable to define dy dt. Again, it's as a function of t and y. Even though t is not in the function, it's only a function of y in this specific problem. We still need the t there. We still need that first, and that's because of how it's called in our Eulersys.m file. So it's basically there's a placeholder so that y will be the second input to the function. Then we have our first element in our vector defining that equation, dy1 dt is equal to y2, and dy2 dt is equal to negative 9 times y1. Then we will call the Euler-Sys function for each of these values of h, h1, and h2, and in each case extract the first column of the matrix, which will give us our solution for y1, since the first element in defining y prime was our dy1 dt. the first column in the matrix will give us the solution to y1. The second column will give us the solution for y2, which in this case, y2 is just the derivative of y1, and it doesn't have any relevance, so we don't care about it. So we won't even solve it. We won't even store that result. Notice I'm just overwriting the variable y_sys each time the Euler-sys function is called. And then just taking our first column of the matrix and storing that in our numerical solutions, ynum1 for h1 and ynum2 for h2, and then lastly calculating values of our exact solution. So let's look at our result, actually plotting those solutions. We see the exact solution is the black line, the analytical solution. Euler's method with two different h values. With h equals 0.01, we see it follows fairly closely. You can see that there is growing error, which we see most at down around t equals 3. We see that that error is growing. We also see, if you look closely here, that the blue dash solution for h equals 0.1 is slightly out of phase. Since this is a periodic cosine function, slightly out of phase with the exact solution. So the error is showing up not just in the magnitude, but also slightly in the phase of that. And that is a result of that forward difference approximation for forward Euler's method. Namely, we're using the slope at the ith point to predict the I+1 data point. And you can see that with the h equals 0.1 solution right at that first value, because the slope of that cosine function at t equals 0 is 0. So right here, those first two data points, you can see where it's going to go out of phase, and we can visually see it for the point h equals 0.1 solution. We also see for the larger time step solution, h equals 0.1, that the solution is growing pretty rapidly. The error is growing to the point where the error here is greater than the solution itself. And we would call that, again, an unstable solution for h equals 0.1. So we don't have an explicit stability criterion that we've developed in this case for the conditional stability of Euler's method on h, but we know that it can be conditional on the step size, and here we see an example where the error grows very quickly for a time step of h equals 0.1 and results in an unstable solution. Before we finish this video, let's look at a couple more examples of writing a higher order differential equation as a system of first order differential equations. So here is the second order differential equation for an RLC circuit, and we can write that as a system of first order equations. We'll say y1 is equal to v and y2 is equal to dv dt, which would be dy1 dt. Then this term, the second derivative of v with respect to t, would be equal to the first derivative of y2, because it's d dt of dv dt, but y2 is dv dt. So that's equal to dy2 dt. So we can rewrite the equation then as L times dy2 dt plus R, and now dv dt is just y2 plus 1 over c times y1, which is v, is equal to f of t. And then writing this in our standard form for Euler's method, again, we would have dy1 dt is equal to y2, and dy2 dt, we have to do a little bit of algebra here, dy2 dt would be equal to 1 over L times f of t, our forcing function, minus r y2 minus 1 over c y1. So let's look at a second example. So here, this would be the result that we could then write as a two-element column vector function in MATLAB to solve this numerically. We can look at the van der Pol equation and do something similar. Again, we'll start by saying y1 is equal to y, and y2 is equal to dy dt. Then, rewriting the equation, we're going to have dy2 dt minus mu times, and that's just a constant, 1 minus y1 squared times dy dt, which we'll substitute in y2, plus y1 equals 0. And you might wonder, well, why didn't we just leave dy1 dt in there? If we left dy1 dt in there, then we'd have two different time derivatives in this equation, and it would make it difficult to separate this out into a system. So leaving that, we want to replace that dy1 dt just with y2, and then we can write this as our system of ODEs as dy1 dt is equal to y2, and dy2 dt is equal to, just solving our differential equation here for dy2 dt, it's going to be mu times 1 minus y1 squared times y2 minus y1. And that's two examples, additional examples, of how to write a higher order differential equation as a system of first order differential equations. And that is a common approach that allows us to develop all of our initial value problem solvers simply to solve a system of first order differential equations, and then we can apply them to higher order differential equations by using this approach.